what we're going to be going over here is an example where we're going to be evaluating some estimated cost functions here using linear regression analysis. So we'll start out here looking at an XY coordinate plot here, or graph here. And we really have two different alternatives here for our cost estimators here. What we're attempting to do here is we're attempting to predict our indirect manufacturing labor dollars here. And I'm showing that as our dependent variable here on our y-axis. And we have those, we have to determine the best cost estimator and really have two different alternatives. First, we could either use the direct manufacturing labor hours here, or we could use machine hours here. Either of those two different alternatives here. And what I've done here is got 12 different data points for each of the alternatives here. So just looking at the data points here, our X1 data points here, those would be for our machine hours, and X2 here would be for our direct manufacturing labor hours. And I've done a linear regression here, a simple linear regression here based on the two different data sets here. So for those blue circles here, those are direct manufacturing labor hours here. And simple linear regression says that, and that's that gold line that I'm showing here with that slope here. And it's saying here that the slope of that line, 7.7 here, times each direct manufacturing labor hour here, X2, and the x-axis here in hours here for those independent variables here, x1 here for our machine hours here, and x2 here for our direct manufacturing labor hours. Okay, so back to our direct manufacturing labor hours here. So take the slope of the line here, that gold line here, is saying that 7.7 times each labor hour here plus 744, that's the y-intercept here, that is going to equal the indirect manufacturing labor cost here based on direct manufacturing labor hours. And then for our machine hours, I'm showing those square green or excuse me, red squares here, and that regression line here is shown in green with that slope here, and that has a slope of 10.3 times each machine hour here plus 300. 300 is the y-intercept here. That would equal our indirect labor cost here. So we got the two different alternatives that we're going to have to evaluate here. And again, these lines here, these straight lines here, or these linear regression lines here, they're based on the least squares method here, where we fitted those two different data sets based on the least squares method here. So what we're going to do is we're going to evaluate these two different cost estimators here, or these regression lines here, to see which one is the best here. Okay, so what we're going to do here, first we're going to be looking at R squared here, and we're going to look at some actual, in this case we're going to be using some Excel regression output here to determine these different, we're going to look at the R squared here, the correlation here between our X independent variable here and our Y dependent variable here, and this is where we're going to be using the F-test here. And secondly, we're going to be looking at a regression analysis. That's if we're looking to see if there's a significant relationship between X, our independent variable here, and our Y dependent variable. So really what we're going to be testing the slope of those lines here, those two different alternatives here, where M is the slope of the line, X would be our hours that we're looking at, and then B here is the y-intercept. And what we're going to be looking at is linear regression using the t-test here. And it'll just be based on a 5% significance level or a 95% confidence level. And again, what I've done here, I've used Excel here, and we're going to be analyzing some Excel data here, where we use the data analysis pack here, and we use the regression function here to determine our different regressions here. And of course, this would be similar for any statistical software. Okay, so let's go in and let's look at our analysis here between our two different cost functions. Now let's look at a comparison between these two independent variables and see which one is a better choice for our model here. So first off, for our X1 independent variable, that represents our machine hours here, and X2 represents our direct manufacturing labor hours, and we'll do a comparison between those two. So first off, we're going to start out with our correlation statistics to see which of the two here is better. So here's where we're going to look at our R squared value and also our standard error here. Okay, to understand what those are, let's just go and get a pictorial here of what we're talking about here. So I've got our XY plot here, our Y predictor value, our dependent variable Y over here, and then our X hours over along our x-axis here. So what we're looking at is each of those 12 different data points or observation that we're looking at, and we're trying to compare them here. So what we would do here, we have our total sums of squares. That comes off our mean value for our y independent or dependent variable here to each of those data points here, and then our residual sums of squares here, RSS. TSS represents total sums of squares. RSS here is our residual sums of squares, and that comes from each of our actual observations to that regression line, that difference squared here. And then our explained sums of squares, that's just coming off our mean value here for our y dependent variable, and that comes based on the regression line here, the actual predicted here on the regression line. Okay, so that's what we're talking about. And if we're looking at r squared, it's really the difference here. If you can look at 1 minus RSS here divided by TSS, that proportion, or it really equals our explained sums of squares here divided by our total sums of squares. So that's what we're talking about with our r squared and our standard error. Okay, so well, the other thing with the standard error is really the variation here between the based on your regression line and your actual data points. That's the variance that you're looking at, that spread here on both sides of the line. Okay, so let's go and let's compare them here. So okay, one other thing here, the r squared here. Here's where we're looking at the correlation, and your r squared is called the coefficient of determination. And this is where you're looking at the proportion of the variation in y, the dependent variable, explained by x here, the independent variable. And that's what we looked at with our diagram here. Okay, so now we can go and look at our r squared here. Okay, let's first off start with that standard error because the r squared gets a bit complicated. So the standard error here for our x1 is 170, and that's that variation that we're looking at here. And a standard error here for x2 is 224. Okay, so you can see that x1 here is clearly better than x2 because we have a lower standard error, 170 versus 224 here. Okay, so standard error, x1 machine hours is a better predictor here. Okay, so now let's look at our r squared values here. So for x1, we got a 0.52, and that's really 52% here. And that's that proportion that we're talking about, the variation in y, the dependent variable, explained by the variation in x, the independent variable. And then for x2 here, we got 16.16 here. That is 16%. So clearly, x1, the machine hours, is much better here. So really, the r squared here, that when you're looking at r squared, they generally look at 30% and above here to be to be a predictor here. But you can see here with the x2, we only have 16%. So you can see it's already failed here. Whereas with our x1, we're sitting at 52%. So really we have sort of a moderate correlation here between our x's and our y's here. Okay, so now let's go and let's test for this r squared. And this is where we're going to use the F test here to prove out our results here. So the first thing we have to do in our F test, we have to determine a critical value here for our F distribution. So let's go and do that here. Okay, so you can either go looking at an F table, or in this case I'm using Excel here, and we're looking at the ANOVA here, and that's really the variation that we're looking at here. So with Excel we use equals, this is the function, equals f.inv.rt here, and then we have to put in what we're looking at here as far as our critical percentage, and we're looking at 5%, and then you have to put in your degrees of freedom here. So we could take our degrees of freedom right off our ANOVA table here, and let's understand that here. And the regressor, that ESS, let's go and look at that. That's what we're talking about, is this difference here between our regression line here and our mean value for our our dependent variable here. And then our residual, that's our RSS, shown here in that green arrow here. And then our total sums of squares, TSS, is shown over here. Okay, and then we have the computer or the software Excel here has calculated our degrees of freedom here for a regressor, our residual, and our total. But let's understand what those are here before we move on here. So you're going to have to know those degrees of freedom to calculate your F-test table here. Okay, so let's go and let's look at what we're talking about here. Okay, so first to determine, you want to determine your degrees of freedom here that you're talking about. So really what we're talking about is that linear regression equation here, is slope times your x independent variable and the y-intercept b here. So k equals our number of degrees of freedom, and n equals the number of observations. In this case, we've got 12 here. So what you want to do here is this here. If you had this regression equation, say you had three different predictors here, x1, x2, and x3 here, and then you have your b, your y-intercept here. So what you're talking about with k, you really have to count up the different coefficients you have for each of those variables. So in this case, b1, or beta 1, beta 2, and beta 3, we'd have k would equal 3 here. Okay, and what we're talking about with these degrees of freedom here, let's just relate to that. So for TSS here, that total sums of squares that we have here, it's really n minus 1. N is the number of observations or data points here, minus 1 here. So for TSS, we had 12 minus 1 gives us 11 here, just as the software package is showing here. And then for our residual sums of squares, let's look at that here. First off, understand TSS, total sums of squares, equals our ESS, explained sums of squares, plus RSS, the residual sums of squares. Just that is the relationship we're looking at. Okay, so back to our RSS here. How do we determine the number of degrees of freedom here, our residuals RSS here at 10? So what we do here is we just take n, the number of data points, and we subtract from that k, the number of different coefficients we have. In this case, we only had one coefficient in our regression equation here. So k is equal to 1 here, and then you add 1 to that here. So in this case, k is 1 plus 1 here, that we get 2. Subtract that from n number of data points here, that 12, and sure enough, we come up with 10 here, degrees of freedom for the residual here. And then for ESS, our regressor here, that's 1 degree of freedom. And let's look at that. So ESS is simply k, our number of k coefficients that we're looking at. So if you had 1, 2, 3 up here, k would equal 3 with 3 different coefficients. We only have 1 here because we're comparing just x1 here versus x2, but each one of them has its own linear equation. So k for our explained sums of squares just equals 1 here. Okay, so that's how you have to work your degrees of freedom here. Okay, so then you go into your, you look at it, based on your degrees of freedom, you either look up at your percentage or critical percentage that you're looking at, and you come up with an F test or F number on it. But in this case, I've got Excel, so I put in 0.05 or 5% here. And the degrees of freedom, 1 comes from our regressor here, and then we have 10 coming from the residual here. So this is the regressor, explains sums of squares. The residual is 10 here for the residual sums of squares. So come in, hit the enter button, and you're going to come up with a value here using the Excel 4.96 for more decimal points here. So that's going to be our critical value that we use here on our F distribution table. You either look it up in some F distribution table or reference table, or you use some software like Excel here to determine your critical value. So we're going to have on our distribution 4.96 is our critical value here. So now we're going to compare our F statistic to it here. So really with the ANOVA here, your F statistic is really your explained sums of squares here, the mean or the mean square for those explained sums of squares here. And that's that ESS here, divided by RSS here. Again, your mean sums of squares, those just your average sums of squares. The ESS divided by RSS, the mean sums of squares here. And we're going to come up with X1, we're going to have an F statistics here of 10.89 here, based on that division here. And then for our X2, our F statistics is 2.04. Okay, so now let's go down and let's make the comparison between the two. Okay, this is how it works. We determine our critical value here at 5% or 95% confidence that we're looking at. And on our distribution here, if we end up with our F value being greater than 4.96, we can accept the fact that we have a relationship here between our X and Y variables here based on that correlation. And sure enough, for x1, our f value is calculated here at 10.894, those observation points. So yes, we pass here for x1. And then for x2, well, what we had? We had 2.04 here. So going to our f distribution, we'll put it on our, plot it on our point here, and it's about there here, f2.04, x2 here. So you can see it didn't pass our critical value here. We're way less on our distribution. So no, our x2 independent variable here does not pass the test, does not pass our critical f distribution test. As you can see with the percentage, the r squared here, at 16%, you can see it's sitting way out here on our f distribution curve. It's way less than our critical value. So no, we can't say we have a relationship with our x2. But with our x1, you can see we're sitting at 52% here. And yes, we did. It had a or a f statistic here of f value of 10.89. Okay, so that's for our ANOVA here, and that's our correlation where we're looking at r squared here, both between x1 and x2. You can either look at a percentage here, but you have to do your test here to make absolutely sure what you're talking about. In this case, we had a critical here of 5% test here. Okay, so that's for our ANOVA here, our correlation here. So next, let's go look at our regression here. And this is, again, looking at it in terms of Excel here. So let's just look at what we talk here. We got our predictor here. We got our coefficients here. And we'll talk about, let's just go down. Our predictors here, we're going to, again, x1 versus x2. And then we got the different variables, x1 variable here in x2 variable. And then we have our intercept here. And then our coefficients here. And you can guess what those are here. So let's just look at x1. Our coefficient, we have 300. We come up with, that's what we have, that b or y-intercept here, 300. And then our m, our slope here, 10.3. That's sitting here, 10.3 times x1 here. Okay, and then for x2 here, our coefficients, our b-intercept here, y-intercept, 744, shown here. And then again, our x variable, x1 here, 7.71. Our m, or our slope, shown here. 7.7, excuse me, shown here. And then the computer were to come up with some standard error here. And what you do is you take, that's your standard error here shown. You take they have taken their standard error for the slope, in this standard error here, the slope m here, and you divide it into each one of the coefficients here. And this is where you're going to come up with a t-stat. And that's what really we're going to be dealing with here. Okay, so we're going to, the other thing is we're not going to deal with the t-stat here for the intercept here, because that's really, it's not a viable determinant here. Really, we want to just look at those two different x1 here and x2, the coefficient based on our linear equation here. So let's just look at we got a t-stat here and a p-value, and we also have some confidence intervals here, 95 lower and upper confidence intervals here. But the key is here that t-stat, and we can also look at it in terms of our p-value here. So for our t-stat for x1, we come up with 3.3 here, and for x2, we have a t-stat of 1.4 here. So let's try to make some sense out of that. Okay, so what we have to go down here, and we have to set up, determine a t-distribution here. With Excel, I'm going to look at it based on two different tails here. So what we have to do is we have to either go to a t-table, and based on some confidence level or percentage here, in this case we're looking at 5%, or you can use, in this case I'm going to use the Excel software here. So the first thing we have to do is go back again and determine our degrees of freedom here. We have to determine what those are. So the degrees of freedom, and then it's going to come into our Excel equation here. Degrees of freedom here for what we're talking about here is n, the number of observations, and we've got 12 here, minus k, the number of coefficients in each of those equations, and we only have one here for each of them. So k equals number, and we got 1 here. So n minus 1, k here, minus another degree of freedom, and that's really for that intercept that we're talking about, that b value. So we got n, 12 points, 1, and then minus 1, k minus 1. So we got up with 12 minus 2 here gives us 10 degrees of freedom. You have to understand how to calculate those 10 degrees of freedom in order to get your t statistic here. You're either coming off some t table, or in this case I'm just using Excel here, or t equals t dot inv dot 2t here, and then 5%, that's what we're looking at our test here, and then 10 degrees of freedom. Hit enter and we're going to come up with a t value of 2.228 here. Okay, so that's going to work into our t distribution here. So those are our critical values, minus 2.28 and plus 2.28. So now we just have to figure out our x2 and our x1 here and our x2 here, x2 where it fits on our t-stat here. We're going to look at a t-stat here and our p-value here. So what we're going to do here, first for our x1 here, our cutoff here was our t-statistic, we recalculated that to be 2.28 here. So for x1, what was it? We had a 3.3 here. T-statistic, we can go look at it here, 3.3. And for x2, we're sitting at 1.4 here. So simply looking at it based on our t-statistic here, you can see with x1, we're sitting here past our cutoff point here. x1 sitting at 3.3 here, past our cutoff point, whereas x2 is sitting here on our curve before our cutoff point here, 1.43. So again, based on our t-stat here, our x1 passes because it's greater than our cutoff point, 3.3 here, greater than our cutoff point, whereas x1 here, or x2, excuse me, is sitting at 1.43 here, less than our critical cutoff point. You can look at it on both sides of the scale here, but that's what we're looking at here. So you can see x2 here fails the test here because therefore we can say we don't have a linear relationship between y and our x2 variable here based on that m slope here. Okay, so that's our t-statistic, and it really works off both sides of the curve here. But then for our p-value, you can look at it here again. Same thing for a p-value. If you look at our x1, we're coming up with 0.8% here. And x2, we got 0.8 here, or 18% here. So just going down to our t-distribution and looking at comparing our x2, we're sitting at 18% here. And for x1, we're sitting at 0.8% over here. And then remember, those critical values here, really based on that was based on that 5% here. So our 5% here is sitting at that. If you went into calculated your p-value, you're going to come, based on your t distribution here, the p-value is going to be sitting right at that cutoff here on your t distribution here. In this case, we're just looking at, you can look at it on either side here, but I'll just look at it based on our minus side here because I got everything filled up here on the plus side here. So we got that 2.28 statistic here, and that relates to a 5% probability p-value here. So you can see with our x1, we're sitting at 0.8% here on our curve here. So that passes our test here. With x2, we're sitting way up here at 18% here. So that's going to fail our test because it's sitting in this 95% region here. So what we've been looking at here with this test, any values that based on our t-distributions that's sitting between this 95% here and each of those cutoffs here, that 2.5% on each side, those tails here, that is anything that's falling on that distribution in this range here fails our test here. That means there is no relation. We can't say that we've got a relationship, an accurate relationship between m, our slope, or those x independent variables versus our y dependent variable. Again, so just showing it down over here. Anything, if lens pass our critical point here on the negative side here, it passes our test. Anything in between the minus 2.28 here, that 95% confidence, any one of the, if the variable value lines on our curve here in between that range, it fails the test. And then again, if it's greater than our critical value here, then it passes the test. In this case, you could see x2 failed the test here, both percentage-wise as a p-value here, and also as the t-statistic here, because it was in this 95% range here. And then x1 passes the test. You could see that here because it's beyond our critical value here. for our t-stat over sitting at 3.3 here, and also for our probability here at 0.8% here, less than 5%. Okay, so that's what we're talking about with our regression statistic here. So you can see here for x1 passes the test, that's saying that we have a relationship here based on that 95% confidence level here, that x1 variable predicts our y in a dependent variable here, whereas x2 does not. Okay, so that's setting up our t-distribution. And then one other thing you can look at, let's go up and let's look at these confidence intervals here. We got a lower 95% and an upper 95%. So if we look at those relative to our statistic over here, our coefficient that we're looking at, not going to pay any attention to this intercept here because that really is not a determining factor here when we're talking about. But for our coefficient, for our x1 here at 10.31, so we have a lower bounds here. It can go as low as 3.35, and on an upper bounds, that slope can go as high as 17.27 here. And then for our x2, this is the case here. This is key here. For our lower bounds on x2, it's a negative 4.3 here. And upper bounds is 19.7. So if we go back and we looked at our statistic here, our slope x2 variable here, m slope, it was sitting at 7.71. So we're saying it can go below, it can go as low as minus 4.3 and as high as 19.73 here. But this is the key here. This is the other thing we can look at. So if one of these statistics, if that range, your confidence interval is, there's 0 sitting between the lower and upper bounds here, or your lower and upper confidence interval here, if 0 sits in here, somewhere in that range, then you don't have a relationship. So for x2, what is our bounds here? It's 3.35 to 17.2. Yeah, because 0 isn't sitting in, we don't encompass 0, isn't in that range, because 0 does not appear in our confidence interval here. We can conclude that we have an x and y linear relationship here. So that's the other thing you want to look at, is those confidence intervals. Look at, see what the range is, and see if you got a 0 in them here. Now, if we go down to x2 variable here, looking at it, you can see we got a minus 4.3, and we go as high as 19.7. But see, 0 does land between the negative range here and 19.7. So this is the case here, because 0 does appear in our confidence interval that we looked at. We can conclude that there's no xy linear relationship here. Okay, so this is just another means of quickly looking at to see if you've got a relationship here. So just to sum things up, our x1, in this case, those were the machine hours here. It seems to prove out on both our f tests, our t tests, and also looking at this confidence interval that we do have a relationship between x1 here, the machine hour predictor, and our y, a dependent variable. We're trying to predict our indirect labor cost here. Whereas with x2 here, you can see based on our direct manufacturing labor hours here, it seems to have failed. It failed all our tests for the f test. That was our correlation test here, and also the r squared here, and we had a higher standard error here for it. And it also failed the t test here based on our t distribution, based on our regression analysis. And it also failed here the relationships that we talked about here, the range relationship. If 0 fell in the range here for that predictor, and we were looking at the slope predictors here. Okay, so that'll pretty much summarize our example here, where we looked at it in terms of some Excel output to get some understanding of how we could make a comparison here between those two different predictors that we're looking at here to determine our y independent variable.